Today we're going to learn how to solve the branch and bound algorithm, how to use the algorithm to solve a pure integer program. It also works on mixed integer programs, just as well. All right, so we're not going to do it totally by hand. We're going to use a graphical calculator to help us with the computations. Okay, so we start with a maximization problem. Example 9, it's on page 513. And z is 8x plus 5y. X plus y less than or equal to 6. 9x plus 5y less than or equal to 45. And x, y are non-negative and integer. All right, so let's start by going to our graphical utility and plugging it in. 8x plus 5y, and our constraints, x plus y less than or equal to 6, 9x plus 5y less than or equal to 45. All right, let's solve. Okay, so our optimal solution is 3.75, 2.25, right over here. And the z value is 41.25. All right, so let's put that on our binary tree that will be used to keep track. It might be best to turn the paper to the side because this tree can get pretty big. I think this might be best. All right, so we have problem number 1. Right, so problem number 1. And for problem number 1, we have z equals 41.25. And we have x is 3.75. Y equals 2.25. All right, so this is problem 1. Now we have to branch. Now we want to focus on one variable, and either the x or the y is a candidate. They're both non-integers. So what we want to do is branch on the two integers that surround the actual value of the decision variable. So why don't we branch on y? So 2.25 is between two integers. So y is less than or equal to 2, and y is greater than or equal to 2. Okay, so far our tree is going to split. We're going to branch on y. Sorry, this is a little mistake here. This should be a 3. All right, so less than or equal to 2, we're cutting off all the numbers, all the y numbers, the y coordinates between 2 and 3. So less than or equal to 2, greater than or equal to 3. That will force y to nudge it towards an integer. All right, so let's see what the picture looks like. So this is two separate problems. So here's problem number 2, and this will be problem number 3. So for problem 2, we add a constraint. So y less than or equal to 2. Let's solve it. Okay, our solution is 41.11, and the x value is 3.89. So, and and y is 2. So as you can see, we nudged y towards an integer, and it did end up being an integer. Now let's try the other branch, y greater than or equal to 3. So let's change this to a y greater than or equal to 3. Solve it. Well, we have an integer. We have z is equal to 39, and x is 3, y is 3. All right, so we've branched into 2 subproblems. So now notice that this is the best integer so far. So best so far. But if you go back to problem number 2, so let's change this to a less than or equal to 2. Notice that the z value is 41.1. The gap is currently 2.11, right? So we currently have a gap, which would be 41.11 minus 39. So it's 2.11. So since the gap is greater than 1, there's room for there to be integers somewhere in problem 2. In fact, since the gap is greater than 0, you could say that there might be an integer hiding in problem 2. See all these lattice points here, all the corners? Any one of them could beat 39. The best we could get in our example would be 40 or 41, and that's what we're hoping for. So we have to keep working, and we have to branch out from here. So y is already an integer, so that's good. So we're going to branch on x. So we can say x is 3.89, so we want to cut off the decimal there. So x less than or equal to 3, x greater than or equal to 4. So we're disallowing 3-point decimal, right? It's either 3 or less or 4 or more. All right, so now remember, from this part of the branch, y less than or equal to 2 will always be in every subproblem. So we have to leave that constraint. Now we add a new constraint. So let's try problem number 4. And this will be problem number 5. Okay, problem number 4, x less than or equal to 3. So let's solve it. All right, we got z equals 34. Not very promising. X is 3, y is 2. Okay, let's try x greater than or equal to 4. Let's try problem number 5. All right, solve it. This looks much better, though still we don't have an integer. Our work is not done yet. So problem number 5, z is equal to 41. X is 4, so we did nudge x toward an integer, but now look what happened to y. Now it's no longer an integer. Y is 1.8. All right. Okay, so we look at what we have so far. Now the gap is 2. So 41 versus 39. And this is dead. It's an integer, but it doesn't even beat the integer so far. So there's nothing to do there. However, there may still be an integer here that will beat 39. We have to search for it. X is an integer, so we branch on Y. So from problem 5, which is the one that's up on the computer screen right here, right? X greater than or equal to 4, Y less than or equal to 2. So now we're going to add a constraint that's going to be strange, because we're going to say Y is less than or equal to 1 on the other hand, and Y is greater than or equal to 2. So Y less than or equal to 1, Y greater than or equal to 2. Notice that we're already assuming Y is less than or equal to 2. So we're basically assuming Y is going to equal 2. So you don't have to worry about it on the computer. It'll take care of that constraint. But this one is more meaningful. All right, so this will be problem 6 and problem 7. All right, so let's see where they take us. So let's try problem 6 first. So Y less than or equal to 1. All right, solve. Okay, so once again, not an integer. So we have Z is 40.56. X is 4.44. Y is 1. Now let's try Y greater than or equal to 2 as the last constraint. All right, infeasible. That means there is no solution. So INF, infeasible. Okay, we're still not done, because there is room, there's still a gap, it's a little smaller, but there is room for there to be another integer point that will beat the 39. So we still have to branch. This time, X is the non-integer. So let's see. So X is less than or equal to 4, right? Take away the decimal and look at the two integers surrounding 4.4. And X is greater than or equal to 5. Okay, so let's go back to problem 6. So that was a Y less than or equal to 1 here. Okay, so now we're going to add, now this will be problem 8 and 9 here. 8 and 9. All right, so X less than or equal to 4. All right, let's solve it. We got 37. So Z is 37. And the integers that we got here are, let's focus a little bit here. All right, so that's a 37, and we have X is 4, Y is 1. Now let's try problem 9. X is greater than or equal to 5. Solve. 40, and we have an integer. So Z is 40, and X is 5, Y is 0. Okay. Now, this is dead, right? That's an integer. There's never going to be anything better than 37. and you already found the integer anyway. This is 39, this is dead. You can't expand an integer solution. That's the best that will ever be. This branch died out, and this branch is gone because this is an integer. And this is your best so far, and the best total. So this is the optimal. So the answer to this problem, and there may be more than one answer, is z is 40, x is 5, y is 0. All right, you can, of course, check your work by going to the integer programming Simplex calculator, which has this all programmed in. So let's give it a try. So z is equal to 8x plus 5y, subject to, so let's write our constraints, x plus y less than or equal to 6, 9x plus 5y less than or equal to 45, and integer x and y. Okay, so it gave us the same solution, and this is essentially the work we did. So as you can see, it looks like they may have chosen to initially branch on a different variable, which might have led to a longer algorithm, a longer iteration. But z equals 40 is the optimal solution. All right, so this is called branch and bound, and this is the most primitive algorithm for solving integer programs. There's much newer methods which are a lot more efficient that are used in real life. So more of that to come later. All right, so take care, everybody. I hope you enjoyed branch and bound. Don't forget to like my videos and subscribe to my channel. Take care. All right, so in the previous lesson, we learned how to solve simple integer programs using the branch and bound algorithm. And as I mentioned, that algorithm is not very efficient for real life problems. And one of the fastest solvers that there are is from Gurobi. It's a very expensive program, but it is free for academics and students. So what are the uses of integer programs? Well, as you can see, they're used in many applications. Whenever you want to optimize things, when you want to make schedules, when you want to do almost anything, shipping, social networking, integer programs are a very powerful tool. Unfortunately, even with the best solvers in the world, some of the really big problems are still unsolvable, but they do solve a good amount of them. So one example is the National Football League. That schedule was solved with Gurobi, with integer programming. And if you look at the full NFL problem, there's quite a lot of constraints, and it's a $5 billion market. So Looking at some of these constraints, there's 256 games. Each team plays 16 games over 17 weeks. Input from all 32 clubs are considered. Television partners have input. Entire process takes 2 to 3 months. So here is the 2013 schedule. And here are some of the rules and goals, some of the constraints. So these would all be coded. Basically, you would be writing a program that would generate all these constraints. All right, so here's another visualization of the schedule. The mixed integer program, 25,000 rows. That means there's 25,000 constraints. 20,000 columns. That means there's 20,000 variables. 800,000 are non-zero. That's in the matrix. If you make a matrix of the 25 by 20,000, 800,000 of the coefficients in that giant matrix would be non-zero. So you solve this integer program. From what I understand, it was solved with many, many computers from around the world, all in parallel. And they generated many, many solutions, and they chose the best one. Another place integer programming is used is in transmission lines. You know, figuring out how to transmit electricity on a high voltage grid. And this optimization is $1 billion integer program. That's how much money can be saved during these things. So in almost any field you can think of, there's probably a way to save money with linear and or integer programming. And in our class, we will learn a few of them.